Video content. AI/ML model, applications in semiconductor manufacturing, process flow. The semiconductor manufacturing process is a complex and multi-step journey. PMP phases in the context of the semiconductor industry. Key components of the diagram in management terms. Explanation of the semiconductor industry process flow diagram. Technical terms. Functional terms. Integration of technical and functional terms. Reports for different levels of management based on targets. Key metrics by target stages. Sample report, raw material procurement. AI/ML model, applications in semiconductor manufacturing, process flow. Pradeep K. Suri. Author, researcher, and AI/ML architect. The semiconductor manufacturing process is a complex and multi-step journey that transforms raw materials into the tiny chips powering modern electronics. Here's a detailed explanation of the process flow. 1. Design and development. Purpose: to create the blueprint for the semiconductor device. Activities: designing the circuitry and layout of the chip using advanced software tools. 2. Raw material. Purpose: to prepare the base material for the semiconductor. Activities: extracting and purifying silicon, which is the primary material used in semiconductors. 3. Wafer fabrication. Purpose: to create the silicon wafer, which serves as the substrate for the semiconductor device. Activities: slicing the purified silicon into thin discs, wafers, and polishing them to a smooth finish. 4. Deposition. Purpose: to add layers of materials onto the wafer. Activities: depositing thin films of materials like silicon dioxide or metal onto the wafer using techniques like chemical vapor deposition, CVD. 5. Lithography. Purpose: to transfer the circuit design onto the wafer. Activities: coating the wafer with a light-sensitive material, photoresist, exposing it to ultraviolet light through a mask, and developing the pattern. 6. Etching. Purpose: to remove unwanted materials from the wafer. Activities: using chemical or plasma etching to create the intricate patterns of the circuit. 7. Wafer inspection. Purpose: to ensure the wafer meets quality standards. Activities: inspecting the wafer for defects using advanced microscopy and other inspection tools. 8. Electrical test. Purpose: to test the functionality of the circuits on the wafer. Activities: performing electrical tests to ensure the circuits are working correctly. 9. Yield analysis. Purpose: to analyze the production yield and identify areas for improvement. Activities: evaluating the number of functional chips produced and identifying defects or inefficiencies. 10. Packaging. Purpose: to protect the semiconductor chip and prepare it for integration into devices. Activities: encapsulating the chip in a protective casing and adding connections for integration. 11. Final testing. Purpose: to perform final quality checks before distribution. Activities: testing the packaged chip to ensure it meets performance specifications. 12. Distribution. Purpose: to deliver the finished semiconductor chips to customers. Activities: packaging the chips for shipment and distributing them to manufacturers of electronic devices. 13. Customer. Purpose: to provide the semiconductor chips to end users. Activities: delivering the chips to companies that will use them in their products. 14. Sustainability feedback and management. Purpose: to gather feedback and manage the environmental impact of the manufacturing process. Activities: collecting feedback from customers and implementing sustainable practices in the production process. 15. Integration. Purpose: to integrate the semiconductor chips into electronic devices. Activities: incorporating the chips into various products like smartphones, computers, and other electronics. 16. Etching. Purpose: to refine the patterns on the wafer. Activities: using etching techniques to further define the circuit patterns and remove any remaining unwanted materials. This comprehensive process flow highlights the intricate and precise steps involved in semiconductor manufacturing, ensuring the production of high-quality and reliable chips. The video represents the semiconductor industry process flow in a structured and visual manner, utilizing a Sankey diagram to showcase the flow of processes and relationships among nodes in the production life cycle. Let me explain it in project management professional, PMP, terms. PMP phases in the context of the semiconductor industry. 1. Initiating phase, design and development. Description: this phase involves defining the project scope and objectives. In the semiconductor industry, it starts with design and development, where specifications for the product are created. Key PMP concepts. Identify stakeholders, example designers, engineers, suppliers. Define high-level requirements and constraints. 2. Planning phase, raw material procurement. Description: ensures proper resource planning, including raw material sourcing for wafer production. Key PMP concepts. Develop the project management plan. Identify risks related to procurement, including supply chain delays. 3. Executing phase, wafer fabrication to wafer inspection. Wafer fabrication, actual production begins here, where raw materials are transformed into wafers. Deposition, lithography, and etching, core manufacturing processes for creating intricate structures. Inspection, ensures quality control and reduces defects. Key PMP concepts. Direct and manage project work. Ensure quality management through control and inspection. Optimize resource allocation to meet deadlines. 4. Monitoring and controlling phase, electrical testing and yield analysis. Description: testing ensures the reliability of semiconductor devices. Key PMP concepts. Perform quality assurance and quality control. Track performance and address deviations. Update risk assessments based on test outcomes. 5. Closing phase, packaging, final testing, and distribution. Description: the final product is packaged and tested before distribution to customers. Key PMP concepts. Formal acceptance by stakeholders or customers. Archive all project documents. Transition the completed product for operational use. Other nodes in PMP terms. 1. Sustainability feedback management. PMP focus, stakeholder engagement and lessons learned. This node ensures continuous improvement and alignment with environmental goals. 2. Customer integration. PMP focus, customer satisfaction and project closure. Feedback from customers guides enhancements for future projects. 3. Etching. A critical step in the process, it reflects the precision work necessary in executing the project plan. Color-coded nodes. Each node and flow is color-coded to highlight processes, individual tasks in the semiconductor industry, example lithography, etching. Flow relationships, dependencies and the impact of each phase on subsequent tasks. This diagram can be viewed as a project life cycle model for semiconductor production, with each step aligning to PMP principles of scope, time, cost, quality, risk, and integration management. Let me know if you'd like to explore specific PMP tools or techniques related to this process flow. Key components of the diagram in management terms. 1. Design and development. Management context, represents the initiation and planning phase. Activities, defining project goals, creating design specifications, and outlining production plans. Objective, ensure that the process aligns with customer requirements and technical feasibility. 2. Raw material procurement. Management context, resource planning phase. Activities, identify suppliers, negotiate contracts, and ensure timely delivery of materials. Objective, prevent bottlenecks by maintaining a smooth supply chain. 3. Wafer fabrication. Management context, execution phase. Activities, process raw materials to create semiconductor wafers, ensuring efficiency and minimal waste. Objective, maintain production timelines while adhering to cost and quality standards. 4. Deposition, lithography, and etching. Management context, core manufacturing operations. Activities. Deposition, apply thin films to wafers. Lithography, pattern the circuits. Etching, remove unnecessary material to define the design. Objective, achieve high precision and minimize defects in production. 5. Wafer inspection. Management context, quality control, QC, phase. Activities: inspect wafers for defects, measure parameters, and ensure compliance with standards. Objective: catch and resolve issues early to avoid downstream problems. 6. Electrical testing. Management context, performance testing phase. Activities: test the electrical functionality of wafers to ensure they meet specifications. Objective: validate performance before moving to the next stage. 7. Yield analysis. Management context, process improvement phase. Activities: analyze production efficiency by evaluating yield, usable units vs total units produced. Objective: identify and address inefficiencies to improve overall output. 8. Packaging and final testing. Management context, product completion phase. Activities: packaging, prepare the product for distribution. Final testing, ensure finished products meet customer specifications. Objective: deliver a fully functional and reliable product. 9. Distribution. Management context, logistics and supply chain management. Activities: transport products to customers or storage facilities. Objective: ensure timely delivery to meet market demand. 10. Customer integration. Management context, stakeholder engagement phase. Activities: collaborate with customers to integrate feedback into the process. Objective: build long-term customer relationships and improve future processes. 11. Sustainability feedback management. Management context, continuous improvement phase. Activities: analyze sustainability metrics and implement eco-friendly practices. Objective: reduce environmental impact and align with corporate social responsibility goals. 12. Etching, separate node. Management context, specialized manufacturing process. Activities: this stage highlights a specific, critical task in the production flow. Objective: ensure precision in design implementation. Flow relationships. Interconnected nodes, highlight dependencies and transitions between stages. Resource management, emphasizes resource allocation across phases to prevent delays. Management summary. The diagram maps the entire production life cycle in the semiconductor industry. It aligns with key management principles. Initiation and planning, establish goals and prepare resources. Execution, carry out production with efficiency and quality assurance. Monitoring and controlling, test and analyze outputs to maintain high standards. Closing, deliver the final product and gather feedback for future improvements. Explanation of the semiconductor industry process flow diagram. The diagram visually represents the process flow in the semiconductor industry, combining technical stages, manufacturing processes, with functional objectives, quality assurance, logistics, and customer interaction. Here's a detailed breakdown in technical and functional terms. Technical terms. 1. Design and development, blue node. Description: the initial stage where semiconductor chips are conceptualized and designed. Technical focus. Define circuit architecture. Use CAD tools for detailed chip designs. Simulate designs to ensure feasibility. Outcome: a ready-to-fabricate design blueprint. 2. Raw material procurement, green node. Description: sourcing raw materials like silicon wafers, chemicals, and metals. Technical focus. Evaluate supplier quality. Ensure purity of raw silicon and dopants. Outcome: high-quality materials for wafer fabrication. 3. Wafer fabrication, purple node. Description: transforming raw silicon into wafers for processing. Technical focus. Crystal growth, Czochralski method. Slicing and polishing wafers. Outcome: pure and uniform silicon wafers ready for chip creation. 4. Deposition, red node. Description: adding thin layers of material, example silicon dioxide, onto the wafer. Technical focus. Use techniques like chemical vapor deposition, CVD. Ensure uniform film thickness and adherence. Outcome: layers for circuit construction. 5. Lithography, pink node. Description, patterning circuits on the wafer. Technical focus. Use photomasks and UV light. Achieve high-resolution patterns using advanced lithography tools, example EUV. Outcome, precisely etched circuits on the wafer. 6. Wafer inspection, cyan node. Description, checking wafers for defects after each step. Technical focus. Use optical inspection systems. Measure dimensions and alignment accuracy. Outcome, early identification of defects. 7. Electrical testing, yellow node. Description, verifying the electrical functionality of chips. Technical focus. Probe testing individual chips. Use automated test equipment. 8. For speed. Outcome, chips validated for functionality. 8. Yield analysis, teal node. Description, assessing production efficiency. Technical focus. Analyze defective units. Use statistical methods to improve yields. Outcome, optimized processes to maximize usable chips. 9. Packaging, dark red node. Description, encasing chips for protection and usability. Technical focus. Bonding wires and applying encapsulation materials. Ensure thermal and electrical performance. Outcome, durable and functional semiconductor packages. 10. Final testing, gray node. Description, ensuring finished products meet specifications. Technical focus. Perform stress and thermal tests. Validate functionality under various conditions. Outcome, verified, ready for market chips. 11. Etching, orange node. Description, removing unwanted material from wafers. Technical focus. Use wet or dry etching techniques. Achieve fine detail without damaging structures. Outcome, sharp and accurate circuit features. Functional terms. 1. Sustainability feedback management, green node. Functional role, collect and implement eco-friendly practices. Objective, reduce waste, energy use, and environmental impact. 2. Customer integration, light blue node. Functional role, collaborate with customers for product customization. Objective, align products with customer needs and feedback. 3. Distribution, yellow node. Functional role, manage supply chain logistics. Objective, deliver chips to clients efficiently and on time. 4. Overall process flow. Functional role, ensure smooth transitions between stages. Objective, maximize efficiency and minimize defects at each step. Integration of technical and functional terms. Technological excellence, each technical stage ensures high-quality semiconductor production. Functional efficiency, functional elements like sustainability and customer integration optimize the business process. Goal, the synergy between technical and functional aspects results in high-quality, eco-friendly, and customer-centric semiconductor products. Reports for different levels of management based on targets. The semiconductor industry's process involves multiple stages, and reports can be tailored to top management, middle management, and operational levels based on their roles, responsibilities, and decision-making needs. Below is a breakdown of possible reports for each management level, aligned with the provided target stages. 1. Top management reports. Focus, strategic oversight, profitability, sustainability, and customer satisfaction. 1. Executive summary report. Overview of key performance metrics for all stages. Includes targets achieved, delays, and major challenges. 2. Cost analysis report. Breakdown of costs incurred at each stage, example raw materials, wafer fabrication, packaging, etc. Highlights cost-saving opportunities. 3. Productivity and yield report. Analysis of wafer yield efficiency and defect rates. Insight into overall production trends. 4. Sustainability report. Metrics on energy consumption, waste reduction, and environmental compliance. Progress on sustainability targets, stage 14. 5. Customer feedback and integration report. Summary of customer satisfaction, complaint resolution times, and feedback-driven improvements, stages 12 and 13. 6. Profitability and market analysis report. Revenue forecasts based on production data. Insights into market demands and customer engagement success. 2. Middle management reports. Focus, tactical planning, resource allocation, and process optimization. 1. Stage-wise target achievement report. Detailed comparison of planned versus actual performance for each stage, targets 1 to 14. Includes reasons for deviations and corrective actions. 2. Resource utilization report. Highlights labor, material, and machine utilization for stages like wafer fabrication, stage 2, and deposition, stage 4. 3. Quality and inspection report. Defect rates and corrective actions during wafer inspection, stage 6. Electrical testing results and failure patterns, stage 7. 4. Process bottleneck report. Identifies delays in stages like lithography, stage 5, or packaging, stage 9. Suggestions for process improvements. 5. Supplier performance report. Evaluation of raw material procurement, stage 1. Lead times, quality compliance, and cost analysis. 6. Distribution and logistics efficiency report. Performance metrics for product distribution, stage 11. On-time delivery rates and supply chain issues. 3. Operational level reports. Focus, day-to-day operations, performance monitoring, and task execution. 1. Daily production report. Outputs achieved for stages like wafer fabrication, stage 2, etching, stage 3, and deposition, stage 4. Shift-wise production stats. 2. Quality control checklists. Inspection results and test logs for stages like wafer inspection, stage 6, and final testing, stage 10. 3. Target progress report. Real-time tracking of stage-wise progress against set targets. 4. Workforce and machine efficiency report. Highlights operator efficiency and machine uptime for critical stages like lithography, stage 5. 5. Inventory report. Stock levels for raw materials, stage 1, and components required for packaging, stage 9. 6. Safety and compliance report. Monitoring safety incidents and compliance with protocols at each stage. Key metrics by target stages. Stage top management focus, middle management focus, operational level focus. Raw material procurement cost, supplier reliability, supplier performance, delivery compliance. Wafer fabrication cost efficiency, resource utilization, daily output. Etching process optimization, error reduction, machine efficiency. Deposition technology upgrade, material usage, process speed. Lithography cost per unit, equipment performance, defect rate. Wafer inspection defect trends, inspection efficiency, test logs. Electrical testing, product reliability testing, accuracy, failure rate. Yield analysis, yield trends, yield improvement plan, scrap reduction. Packaging supply chain alignment, packaging line efficiency, packaging rate. Final testing, product certification readiness, error reduction, pass/fail log. Distribution logistics cost, delivery timeliness, shipment accuracy. Customer engagement, customer retention metrics, issue resolution time, customer feedback logging. Feedback integration, strategic feedback utilization, integration plan, feedback recording. Sustainability, environmental compliance goals, energy and waste reduction targets, daily monitoring. Suggested report formats. 1. Top management, high-level dashboards, graphs, and summary KPIs. 2. Middle management, detailed tabular reports with trend analysis. 3. Operational level, daily/real-time logs and task-specific metrics. Sample report, raw material procurement. This bar chart, titled Pradeep K. Suri, 2025 Forecast, Raw Material Procurement, Semiconductor Industry, provides a comparison of raw material procurement across 3 different years, historical 2023, historical 2024, and forecasted 2025. Here's a detailed breakdown. Key components. X-axis, months, represents the months from January to June. Y-axis, metric tons, measures the quantity of raw materials procured, ranging from 0 to 140 metric tons. Bars. Gray bars represent the historical procurement data for 2023. Dark blue bars represent the historical procurement data for 2024. Light blue bars represent the forecasted procurement for 2025. Monthly breakdown. 1 January 2023 procurement, approximately 60 metric tons, gray bar. 2024 procurement, approximately 80 metric tons, dark blue bar. 2025 forecasted procurement, approximately 100 metric tons, light blue bar. 2 February 2023 procurement, approximately 70 metric tons. 2024 procurement, approximately 90 metric tons. 2025 forecasted procurement, approximately 110 metric tons. 3 March 2023 procurement, approximately 80 metric tons. 2024 procurement, approximately 100 metric tons. 2025 forecasted procurement, approximately 120 metric tons. 4 April 2023 procurement, approximately 85 metric tons. 2024 procurement, approximately 105 metric tons. 2025 forecasted procurement, approximately 125 metric tons. 5 May 2023 procurement, approximately 90 metric tons. 2024 procurement, approximately 110 metric tons. 2025 forecasted procurement, approximately 130 metric tons. 6 June 2023 procurement, approximately 100 metric tons. 2024 procurement, approximately 120 metric tons. 2025 forecasted procurement, approximately 140 metric tons. Observations. Increasing trend. The chart shows an increasing trend in raw material procurement from January to June for all 3 years. 2025 forecast. The forecasted procurement for 2025 is generally higher than the historical data for 2023 and 2024, indicating an expected increase in raw material needs for the semiconductor industry. Comparative analysis. Each month's comparison between the 3 years highlights a consistent growth pattern, with significant increases forecasted for 2025. Summary. This bar chart effectively illustrates the growth in raw material procurement in the semiconductor industry over 3 years, with a notable increase forecasted for 2025. This indicates an anticipated rise in production demand and possibly an expansion in the industry's capacity. Thank you.